Today, I'm going to talk about a classification of a 3+1 dimensional topological order. In this seminar series, we heard a lot about the symmetry, the generalized symmetry, higher symmetry, non-invertible symmetry, and etc. So it turns out that those symmetries, this particular generalized symmetry, may not be described by a group or higher group. Instead, a symmetry is described by a topological order in one higher dimension. And actually, there's a lot of equivalent theory. So the symmetry can be viewed as a non-invertible gravitational anomaly, or the symmetry and its dual symmetry can be put together and to get a more complete description, and which corresponds to topological order in one higher dimension, which is also a non-degenerate braided fusion category. And there's also a algebra of local symmetry operator point of view. So there's also the braided fusion category hidden in the algebra of local symmetry operator. So all those development kind of led to the picture that the symmetry there's a more general way to describe the symmetry rather than using a group. So instead of discussing those connections on this new point of view of symmetry, today I will concentrate on the topological order in one higher dimension. So in this respect, it describes a symmetry in one lower dimension. So you can view topological order as a replacement group theory, which describes symmetry in one lower dimension. So in particular, the topological order in 3+1 dimension discussed today will describe a symmetry in 2+1 dimension. So what is topological order? Topological order basically is the equivalent class of a gapped quantum system. So let me just quickly review what is a quantum system, what is a gapped state. A quantum system defined by a Hilbert space and a Hamiltonian Hermitian operator acting on the Hilbert space. But however, in many-body physics, in condensed matter physics, we always discuss system. And in certain dimension, this concept of local and the dimensionality of a system is embedded in the tensor product decomposition of the Hilbert space. So the Hilbert space can be written as a direct product of many smaller Hilbert space. And this smaller Hilbert space can be assigned to the a vertex. And this vertex form a graph. So they have a sense of neighborhood, a near vertex, further vertex. And that's give rise to the notion for dimension. So this Hilbert space with tensor product decomposition is so-called a local quantum system. And the Hamiltonian is some of the local operator which act on a single small Hilbert space or in some several small Hilbert space nearby. And usually a ground state is referred as a lowest energy states, the state with the smallest eigenvalue of this Hermitian operator. But actually, in physics, we usually refer to ground state as this linearly degenerate subspace, which is separated from rest spectrum by a big energy gap. So this is a notion of a gapped state. The gapped state is that we have a window in the spectrum, and below the window there's a nearly degenerate state. Therefore, to say things more precisely, actually, the notion of a gap is not a property of a single system, but the concept of a n go to infinite limit, where n is the number of vertex. And when n go to infinite limit, this splitting of low energy space becomes smaller and smaller, but this window remains finite. And this nearly degenerate ground state from this low energy subspace, which is more precisely referred as a gapped state. Okay, and then to define gapped phase, quantum phase, we need to define the equivalence relation between gapped state. And this gapped state, this equivalent relation is given by this adiabatic evolution. So we're using this Hermitian operator, which is sum of local operator to define a unitary operator, which rotate this low energy subspace in a nearly degenerate subspace. And if the two nearly degenerate subspace can rotate into each other via this local Hamiltonian, then we say they are equivalent. Okay, and in modern days, in quantum information age, people also write this adiabatic deformation as this discrete layer of local unit transformations. And so this became a local unitary quantum circuit. So this adiabatic evolution is also local unit quantum circuit. So therefore, two low energy states connected by the local unitary transformation was regarded as equivalence, and this equivalent class gave rise the gapped quantum phase. So the picture really the following: in a sequence of n go to infinity, and we can have we have two sequences of n go to infinity, and for each n there's a local unitary equivalence, and this define the gapped quantum phase, and which in some sense define the topological order. So this is a microscopic definition of topological order, but this definition have a problem. You know, it's okay for translation invariant system, but if system have no translation symmetry, it's hard to enlarge the system. Because if you enlarge the system, if you double the system, maybe one half system is quantum Hall state, another half is a ferromagnetic states. So it's a non-invariant system. There's a problem with this. So this problem is fixed by generalize this equivalence relation. We say the two quantum states with different size can be viewed as equivalence. If one quantum state with bigger size is a smaller quantum state tensor product with a product states. So this DP is a direct product states. It's just a tensor product states of states on each small vector space. Okay, so this will be part of equivalence relation. Then plus its local unitary, they define a bigger equivalence relation, and then the system with the different size are connected. So this actually is a microscopic definition of a topological order. So in some sense, a topological order have a kind of precise definition using microscopic theory defined on the lattice. And nowadays, we think this topological order is should be related to the so-called fully extended quantum topological quantum field theory, or some kind of braided fusion category theory. So those topological quantum field theory and braided fusion category somehow is defined for the continuous space or continuous manifold. Okay, but this microscopic definition of topological order is defined on the lattice on the graph. So the connection between these two definitions already touch a very basic question: how the structure of manifold emerge from a graph, from discrete graph. So this is the famous problem in quantum gravity. But even in topological phase, this kind of issue appears.
Xiaogang, can I ask a quick question? You kind of already addressed it, but I just want to ask for clarification. So what are the assumptions you made on the graph here? I guess you need some notion of locality or some notion of dimensionality, right? A general graph has no such notions. So
indeed, the graph here the graph is right. So the graph I'm thinking about is I think have more conditions, so that is can locally approximate somehow resemble the manifold. So basically, at least one should have every vertex have a finite number of edge, every edge have finite number of triangle, and also there's some other things you should not have a dangling triangle attaching arbitrarily. There's something which is something there, yeah. But I think most important thing is there's some connectivity thing, yeah. I don't know enough of graph theory to really describe this general formulation.
But since you also mentioned phases, the general graph doesn't even have the notion of phases. A graph is just made of vertices and edges. So I guess you actually have
Basically, I like to have a graph which have enough structure we can define the dimension of the graph, which have integer dimension.
Okay.
And this is important actually. So graph should have certain regularity, which is so that the dimension is somehow well defined. And the graph is more general, so you have a graph with have a fractal shape, and so then you're totally right. So there should be something about that.
Okay, all right, thank you.
Thank you. Okay, so this is just a microscopic definition, and today I will mainly concentrate on this macroscopic description of topological order. So basically, the proposal is that the topological order are described by this topological extension over the ground states, and those topological extensions are described by so-called the braid diffusion category. It turns out that the braid diffusion category, this category theory, happen to be the right language to describe a topological excitation or any excitations. Okay, so in 3 dimensions, we can have a string-like excitation, and so which we call the associated with a simple object. And this one morphism would correspond to point-like excitation. So in this picture, so this surface is a word sheet of a string-like excitation, and this line here is a word line of point-like excitation. And so you can see that this line separate to word sheet is a one morphism and things like that. The two morphism in this braid diffusion 2 category would correspond to this local unitary operators. And so this excitation can fuse, can braid, so that gives us a braid diffusion category. So therefore, we think maybe the topological order is very closely related to the braid diffusion 2 category.
May I ask another question?
Yeah.
Earlier you emphasized hi Xiaogang, by the way.
Yeah, sure. Hi.
Earlier you emphasized that you really need to take n to be large, the number of sites.
Yes.
But I think you need more assumptions. First of all, you need, as Shuheng said, it depends how you take in more structure of the graph. Like, I assume you want the graph to be, the density goes to infinity, but also to be a finer and finer mesh, but in all possible directions. If you have, you cannot just add more and more sites in the x direction, but not more in the y direction. So it's not simply taking n to infinity. You need more restrictions on that, and that depends on assuming more information about how the graph is related to an underlying manifold.
I hope
so
there's a
graph
local description
n1 times n2 sites. You can send n1 to infinity holding n2 fixed, and then that's probably not good enough because you need both n1 and n2 to go to infinity.
You are totally right. Yes. So actually,
the other thing is that it might also be that the limit depends on how you take n to infinity. For example, through even numbers, through prime numbers, and so forth. And that could affect the answer. And I don't see that in your definition. I think what you have in mind is that there is a well-defined limit where n in all possible direction goes to infinity. And it does not depend on how we take the limit.
Yeah. So there's maybe let me remark on this too. First, we don't have a symmetry. And also, I said n1, n2 in different direction go to infinity in different rate. It turns out that this ability to dissolve, we call dissolve tensor product state. Your product state is very important because when you have a gap states which can dissolve these product states, the metric became unimportant. So this really gave rise to this liquid notion of liquid phase. And so therefore, so basically, so the nx, ny, they go to infinity with different rate, different speed, do not affect problem here because of because this condition is very strong, make things topological.
No, but imagine N1 doesn't go to, N1 is held fixed and N2 goes to infinity. That's clearly not good enough.
Yeah, that's not good enough. Yeah,
and it might also happen that taking N1 through even numbers to infinity and taking N2 through numbers that are a 1 mod 13 will give a different answer.
Yeah.
So I think you need more assumptions to.
Yeah. And for the second question, whether N is some, so indeed there's one assumption. It's actually very interesting. That is there should be a sequence of Ni which go to infinity, and this is defined for the particular sequence. And then there is an issue about the different sequence may define different things actually. And I don't know whether I don't have an example without symmetry whether this particular, whether one need to take a particular sequence of Ni or not. Certainly with the symmetry, one need to pick a particular sequence which coupled with the symmetry. So indeed, this part is there's a lot of subtlety in this microscopic definition, indeed. And but what I really try to point out is that this local unitary and this ability to dissolve product states, I feel this is a two key point. Other point would be it's about really about this graph and what kind of sequence one should take for this graph. Yeah. So this is actually within this definition. If you go through these subtleties, you will discover the fraction phase actually. And so actually fraction phase actually this ability to dissolve product state is a condition which rule out the fraction phase. Yeah. Okay, so let's please.
Does this mean that only the gauge fluxes are your simple objects? So unlike in 2+1D.
Oh, I will come back to that. So what is a topological extension? You can see if you use some topological extension to describe topological order. So what is topological extension? So here we say that remember the ground state is defined by some Hamiltonian H0. So I have an energy gap. The excitation is defined by original Hamiltonian plus traps. We can imagine there's some Hamiltonian term. Delta H only acts on locally near a point or locally near the loop. So the Hamiltonian with the trap also have a gap. And the degenerate ground state of below the gap is called this topological extension, or more precisely, actually correspond to the home space of a category theory. So this is degenerate subspace. Certainly, we take a limit with the system that go to infinity. When you have a loop, the loop size go to very large. Okay, so this is kind of the home space. But however, here there's an important detail: whether the trap Hamiltonian to be local or non-local around the string. So for the point, it doesn't matter. The local, non-local is the same. But when you have a string like an extension, whether this trap Hamiltonian can be chosen to be local or non-local, is around the string. So if you actually this if you choose a local Hamiltonian, we can also define equivalence relation. We can deform the local Hamiltonian so that this gap do not close, and those give rise to the equivalent class of extension. And that defines a type of extension. Or you can use a non-local Hamiltonian and using the deformation of non-local Hamiltonian while keeping the gap, which defines the elementary type. So actually, there's a difference between type and elementary type. And this defined via local and non-local Hamiltonian. So the question you raised, like in the gauge theory, the gauge flux actually correspond to elementary type, I think. So this really is a subtlety in higher dimension, and also in gauge theory, there's also a descendant extension, which is not elementary type, which is basically like a condensation of some point-like excitation around the line or around the surface, they may form quantum Hall states or ferromagnetic states, SPD states, and etc. So those string-like or membrane-like excitation formed by those lower dimensional excitation is called a descendant excitation. And so the type of excitation would include this descendant excitation and also this elementary type. Okay. The one way to distinguish these two excitation is that this elementary type excitation, say two excitation with different elementary type, do not have a domain wall connecting them. So there's no morphism connecting them. But however, the two excitation differ by the descendant excitation. There's always a domain wall connecting them. But however, this domain wall can be gapped or can be gapless. So this so there's a lot of subtlety in the definition of topological excitation. So that actually that have impact on what kind of category theory we should use to describe the topological order. So this question, I don't know, may not be fully resolved. So this is a subtlety. Okay, so for example, in one dimension, we believe that there's no non-trivial topological order, and all the excitation in one-dimensional space is a point-like. So there's no distinction of elementary type or type. So they just they only have there are no topological order, so there's only a trivial excitation, no other excitation. In two-dimensional space, we believe that the topological order are classified by the unitary modular tensor category, and the times z. This z is described invertible topology generated by the E8 states. And there's only one trivial type of string-like excitation. And because we don't have symmetry, there's no topological order, so there's no non-trivial one-dimensional phase. So therefore, the string-like excitation only have one trivial type. And certainly, there's also trivial elementary type. And the point-like excitation, there can be non-trivial one, which is a modular tensor category. In three-dimensional topological order, in three-dimensional space, the topological order classifies something, which we're going to discuss today. And here something interesting happens. There's an infinite type of a membrane-like descendant excitation, because we can using the trivial excitation to make a quantum Hall states. So we have infinite number of quantum Hall states. And they all have a gapless boundary. They don't have they only have a gapless boundary for the chiral quantum Hall states. And certainly we can also using this trivial excitation to make a topological model or some other quantum double model. So there's also a membrane-like excitation with a gapped boundary. So there's a important thing is that whether the category theory describing 3D topological order should allow membrane excitation with only gapless boundary or not. So this is the one of issue. And from physical point of view, looks like yes, but from mathematical point of view, seems it's kind of difficult to include those kind of membrane excitation with a gapless boundary only.
Sorry, Chuck, I missed one point. So in 3D space, you talk about a membrane-like descendant. But what about in 2D space? There are also things like that, but you didn't think to.
In 2D space, there's a string-like, but there's no non-trivial phase of string-like excitation.
But there are descendants, right?
No, descendant, they are trivial. They all belong to trivial class of descendant. So the non-trivial phase on the membrane belong to non-trivial class of a descendant.
Oh, I see. I see. Can you say again? How do you define the class? Is it?
Class means in physics it means a phase. If you're using local unity transformation to connect two membrane, they belong to the same class.
I see. I'm with you now. Okay, thank you. I see.
And for the string and the point-like excitation in three-dimensional space, there's non-trivial type, also non-trivial elementary type. So this is a kind of some subtlety in three-dimensional space. And certainly the braided fusion category do not really classify topological order because there's invertible topological order. For the so let me just go through this quickly. For invertible topological order, there's no bulk excitation, and braid fusion category describe a bulk excitation. So therefore, the braid fusion category cannot see invertible topological order. But however, we believe that in 3+1 dimension, there's no invertible topological order. So we don't have such issue. So therefore, in 3+1 dimension, it's okay. This invertible topological order. It's not an issue. We can use a braid fusion category to classify topological order. Okay, so let's try to see what is the structure of 3+1D topological order, or in terms of what is structure for this braid diffusion category, braid diffusion 2 category. Basically, the 2 category basically means that you have a string excitation and there's a particle excitation, and they can fuse and braid. But in 3 dimension, the braiding of a particle is very simple, because in 3 dimension, we can only have a boson and a fermion. And in particular, moving one particle around another particle by 2 pi is nothing. And so they always have a trivial mutual statistics. So the trivial mutual statistics tell us that this particle form so-called symmetric fusion category. So this is a fancy way to say everything have a trivial mutual statistics. And also due to Danaga duality, this symmetric fusion category is always associated with a finite group. So this symmetric fusion category can be viewed as a fusion of a representation of a finite group. So therefore, the particle in 3-dimensional topological order always give us a finite group. So we already have a finite group. We call it a G. Okay, and but however, the symmetric fusion category also have 2 versions, because it have a trivial mutual statistics, but the self statistics can be boson fermions. So if a self statistics, if every excitation, if all the point excitation are bosons, then this is symmetric fusion category are really just representation theory of a group. If some particle are fermions, then this symmetric fusion category is a graded the super representation of a group. So this group would have a Z2 center and this Z2 center representation with non-trivial Z2F would correspond to fermions. So therefore, the 3+1D topological order would already contain a group or this kind of a graded group. So describing for the boson case or fermion case. So let's consider these 2 cases separately. And so the key to understand the 3D topology now is just to see what is the strings and what is structure of string, how the particle and string combine together. So basically, there's two things we are going to use.
Excuse me, Xiaodao.
Yeah, please.
How about the braiding between strings or multiple strings?
Yes, it have that. Yes.
You only describe particle and string braiding here.
Yeah, so I'm going to describe string now. So far I only described particle braiding. I did not touch string braiding. And you are right. The braiding between strings is complicated, and it seems it's pretty difficult to understand the braiding between strings. So what I try to do is that I try to avoid this problem, find a way to avoid this problem, not to discussing braiding between strings. So the two conjecture, or maybe 2 things we are going to use, which we believe, but probably may not be proven rigorously. One is this so-called remote detectability principle. That is anomaly-free topological order. Again, anomaly-free here really means something realizable by lattice model. Here I use a definition. Realizable by lattice model in the same dimension means anomaly-free. Okay. Then for the anomaly-free topological order, every elementary type of excitation can be detected by other excitation via some kind of remote operation like a braiding. So this is how we detect a loop excitation using a particle braiding. And then there's also anomalous topological order. So there are topological order which do not satisfy this condition. But however, we believe that those anomalous topological order are always realizable by the boundary of some 1 higher dimensional anomaly-free topological order. So basically, this braid fusion category describing excitation in anomalous topological order, which we denote as R. Actually, this R have a center or bulk, which gave rise to the non-degenerate diffusion category, which describes topology order in one higher dimension. And we believe that such connection is a one to many. So basically, this boundary topology order R uniquely determine the bulk topology order. But a given bulk topology order, they can have many boundary topology order, but the boundary uniquely determine bulk. So these are two things we feel is most important that we can use in these two property to determine the 3+1D topology order without using too much of loop braiding. The loop braiding is more complicated.
Xiaogang, so a quick question. So do the higher categories in the previous slide, do they contain the descendants or not?
Yes, actually, to have a more complete definition of all this notion for center and all this category, one need to contain descendant. Actually, this is a very important work by Theo and Giotto, and they had a convention completion. And so after this convention completion, one can define this structure more rigorously.
But 3+1D and higher, does that mean it has infinitely many objects? Because as you commented earlier,
exactly. Yeah. So thank you for the question. Actually, this is the one thing which I myself kind of confused about. Even for the trivial topology order in higher dimension,
right,
it have a infinite number of descendant extension.
That's right.
Actually, the descendant extension in higher dimension topology order classify all the topology order in lower dimension.
Mm-hmm. Yeah. And
so knowing the structure of descendant extension in higher dimension topology order, then we know everything. So that's n vec. If you know n vec, we know everything. But there's a issue whether n vec contain descendant extension which do not allow gap boundary or not. This became an issue. Because including descendant extension which do not allow gap boundary is difficult. And because my understanding that currently the mathematical definition, those kind of descendant extension with only gapless boundary, I think is not included. But you know, I don't know enough math to really see it. But this subtlety bothers me. Yeah. So actually there's a program driven by Liang Kong and Hao Zheng. They really try to include the gapless states in the picture. So therefore to have a complete theory of this higher category theory for topology in a higher dimension, one probably necessarily include the gapless states. Problem cannot avoid that. But avoiding that maybe also give you consistent mathematical theory. You know, what I try to say that there's another way to define descending extension. We only include descending extension with a gapped boundary. And that's maybe enough to define a consistent mathematical theory, some higher category theory. But this theory may not be what exactly corresponds to physics definition of topology order, which I gave in the microscopic sense. Yeah. So there's a lot of progress. Maybe there's still a small gap. Yeah.
Okay. Thank you.
Yeah. Can I ask a question?
Yeah, sure.
Yeah. So regarding this definition of elementary type of topological excitations, when you say a topological excitation, do you include things like defects? But when you say, for example, in 2D space, there's only one elementary type of string, I guess you are excluding, for example, these non-trivial invertible domain walls. Is that the correct understanding of the statement?
There's no invertible domain wall because of no symmetry.
But given the TKFT, it might have some intrinsic symmetries. You can construct domain wall that permutes.
Yeah. So here. Okay. Yeah. That's let me see. Is this
Chenmo, maybe I can answer your question.
Sure.
I think the symmetric defect one is the condensation descendant in Xiaogang's setup.
Yeah.
Oh, okay.
Yeah, it's connected to the non-trivial one by introduce a twist defect, right?
Well, I guess my question is, do you include twist defects in this topological excitation? Or maybe I didn't quite get what you.
I guess when Xiaogang mean elementary, then you don't include it. But if you include the condensation descendant, it is included.
Yeah.
Okay.
So you're totally right. It's thank you for this question. Actually, there's a one thing. It's really about this definition. You can see when you're adding this traps, which define string-like excitation, and so there's an issue. What can be realized by the trap? So one thing one can say that this trap probably do not realize the main wall between two different topological order.
Sure. Yeah.
So I don't know this. Actually, the question you asked is a very good question. Whether this permutation anion, this kind of domain wall can be realized by the trap without modifying the Hamiltonian on the two sides. Or maybe this is a more dedicated question. Yeah, indeed, this is a very good question.
I think twist defects.
I have a somewhat related question. I don't understand what kind of symmetries you assume exist.
No symmetry at all.
No symmetry. But it's often the case that the TQFT that you get at long distances has its own symmetries.
Yes,
even
that's
though
right.
they are not present on the lattice. For example, in the Tori code, we have a Z2 times Z2 one-form symmetry, the TQFT, which does not exist on the lattice. But that allows you to have more defects along the line that Mong had in mind. All sorts of other things, even though the microscopic theory does not have the symmetry. So you should be able to accommodate them because they're clearly properties of the system.
So the thing that whether this the question is really whether those the main wall or those line are they stable along this by this deformation, because we have this lattice Hamiltonian which can excite these high energy excitations. They can deform each other basically, and when you have a non-trivial topological order, as I mentioned, that then there's we have non-trivial topological orders. Actually, those point-like excitation have this emergent symmetry. They can form this descendant excitation. So that's why in three-dimensional topological order, there's a lot of descendant excitation on the string and on the membrane, which are formed by the gauge charge, for example. And the gauge charge have emergent symmetries, and so therefore those descendant excitation would have this SPD states and would also have this topological order states. And those kind of things would exist. Okay, so the point is that we try to so let's consider a simpler case, which is the topological order with only this all the particle is only bosons. So suppose this particle there's no fermion, all the particle like excitation are bosons. So here the claim is that this kind of topology are described as so-called one-to-one classified by so-called pointed fusion two category with only trivial morphism. And this kind of pointed fusion two category is given by this pair, a finite group and H upper 4 cocycle. So this basic diagram we can model. So the idea is that certainly we assume there's no non-trivial, no invertible topological order, and also the key step in the argument is that each of these is all boson topological order have a unique gap or string boundary. So boundary only have a string, no particle, no non-trivial particle. Then the string on the boundary have a point diffusion rule. So all the string have quantity dimension 1. And they form a group. This point diffusion rule define the fusion group, this group. And this group on the boundary for the boundary string is equal to the group for the bulk given by this Tanaka duality of a particle fusion. Okay. And so this basically is an argument. So certainly there's the topological order also have all particle boundary in 3+1D, but we find this all particle boundary of 3D topological order is called a pre-modular tensor category, and this all particle boundary is not very convenient. So we kind of try to avoid this using this all particle boundary to describe topological order. We try to using all string boundary. Okay, so how to construct an all string boundary? And the way to construct all string boundary is basically we try to condense all the particle like excitation. Yeah. Then if you condense all the particle excitation, then you change the topological order to another topological order. And this new topological order, because all the particles are boson, they are all condensed. So the new topological have no particle, have only strings. And here is one thing is that we try to show that this string only topological order in 3+1 dimension must be trivial. Okay, and so there's an argument. So we consider loop this S1, this loop S1 is our string excitation. We just put this S1 in a space. We assume space is S3, and then we say that if this S1 is non-trivial, it must be detectable by something else. But we only have a string, so this S1 embedded in a 3-dimensional sphere must be detectable by another loop. Okay, and these two loops can braid like this. Okay, and then you can shrink the inner radius of the loop, make it a very small loop. And then this braiding process can be viewed as a small loop going through this to the middle of the first loop, and then braid through. And because the space is 3D sphere, this can be viewed as a small loop go around our original loop. But the small loop can be viewed as a particle, and all the particles are trivial. So this became a trivial particle braid with a small loop, original loop, which is a trivial. Okay. So therefore, so this should say, yeah, we have nothing to detect this non-trivial string, and so this is the argument to say that if you condense all the bosonic point like excitation, and we should get a trivial excitation. So this actually is you can say it's a conjecture, and so that's a wonderful conjecture we use.
I think there's a question in the Jude, please go ahead.
I try to understand the remote detectability, and also the statement here. Is it possible just have a topological order in 3+1D that have a string excitations, and they can be detected by braiding only through multiple strings, not the two strings process you described here? It seems like you are exclude those cases, right?
Yeah, here I try to argue each of the string, each loop string must be trivial. Yeah, indeed, we only argue that, and then we say that. So then we try using to argue that there's no non-trivial string, because if yeah.
But it seems maybe is it assumption or it's proven? It seems to me it's an assumption. Because
it is an assumption, I don't want to honestly. This argument is very strong, but this is a assumption. You can say this is an assumption that we try to say that this the loop only topological order is particular if there's no particle. If there's no particle, the loop only topological order is a trivial.
I could hypothesize. I don't know whether you can rule out, say, just one type of strings, and the strings only 3 of them braid through this 3-loop braiding can give some non-trivial statistics, and they will not be captured by what you described here.
No, yeah,
right. Okay.
Yeah. But the thing that the 3-loop braiding actually really describing non-trivial dimension reduction. Yeah. And
yeah, but there are maybe some other types of string braiding.
I wanted to ask whether 3-loop braiding counts as remote because they're sort of still linked together, right?
They don't touch. The remote means this particle never come close to the loop. So our probe is very far away from what we detected.
So you'd still count 3-loop braiding as a remote.
Yeah, the remote. They don't because the string never come close to each other. So 3-loop braiding should be viewed as a remote. Yeah.
But following up on this question, Xiaogang, can you give us some intuition why you think there's no consistent topological order with only strings and they only braid non-trivially through 3-loop braiding? Because the on your slide doesn't apply, right? Because in the 3-loop braiding, you will have a third string piercing through the center of the 2 of them, and then you cannot shrink S2 to make it a particle.
No, you cannot. Yeah.
So I'm curious about what's your intuition behind that.
The intuition is really that I feel that I don't have too much intuition here. I feel that this in order for string to be non-trivial, I think you can detect a single loop. I feel that this a single loop in S3 should be detectable.
I feel like this is assumption, not the.
Yeah, this assumption. Yeah, this is assumption.
I think it's a simplification.
This assumption.
Yeah. Okay. Yeah, thanks.
Yeah. So there's this is an assumption built into this argument, and so basically that's the purpose of this talk. I try to expose all these assumptions and in this argument, There's also dimension reduction. I think we can also use a dimension reduction to consider this, and which may give similar results. Yeah, it gives the same result. Let me say, and so therefore, if you condense all the point-like extension, then we will get a trivial topological order. The domain wall between trivial topological order and non-trivial topological order would only have a string because all the particles condensed. So this is how we get this particle only boundary. Okay. So then how to understand this? How to get a string only boundary? So how to understand this string only boundary? And again, there's a conjecture or assumption, because we need to understand what is a simple excitation, and means stable excitation without accidental degeneracy. And here we assume that if we can consider a loop excitation, loop-like excitation have a topology of S1, a loop. If you shrink this loop and to get an identity, maybe multiple identity, and then we say that this loop is simple with only if n equal to 1. Okay, and certainly the loop may shrink to something do not contain identity, and that means that this loop actually carry gauge charge. So we don't consider that case. We consider this a loop which have neutral charge. It can get identity, but the multiple identity means the loop is non-simple. And this again for motivation that in 0 dimension, S0 actually has 2 points. It's basically a particle and anti-particle. And when you shrink this S0 into a point, and we get a single identity, that's condition for the I to be simple. And also for example, in 3+1, in S3 gauge theory, in 3+1 dimension, we find that there's a A1, A2 just repetition for S3, which are charged. And S3 also have a two conjugate class describe flux, which are B and C. And both B and C, when they shrink, they get single identity. And so these things are kind of consistent. So we kind of assume this is another assumption we use. And
so this all-string boundary may not always exist, right?
What?
The all-string boundary may not exist for
they
every.
Exist. No. In this case, that exists. For the AB topological order, they always exist. This is what I try to argue. When you condense all the particles, you get a trivial phase. Then the boundary between this particular condensation-induced boundary is the all-string boundary.
Thank you.
The boundary produced by condensing all the particles. Because particles are bosons, we can condensing all of them. Okay. So let's consider the string and the bulk. So we have a loop in the bulk. And if they shrink, they can shrink into the trivial particle and some ij non-trivial particle. So the S is a string. Okay, when they shrink, you get this. But when you bring this string to the boundary, it may become string may become a direct sum of several other strings on the boundary string. So H is a boundary string. This is possible. So here I try to say that the simple string on the boundary H should shrink to 1. If they shrink to n minus n1, n copy of 1, they will be not simple. Okay. So therefore, from here we can see that this simple string on the boundary, they all have this they have this dimension 1. Okay. If they have the quantity dimension 1, and then the reason is that on the boundary they can only shrink to 1. There's no other particle-like extension. So therefore, when the shrink loop to the boundary, the only thing we can have is a 1, a trivial particle. And this trivial particle should only appear once if this boundary string is simple. Okay. So this led to the argument that the fusion rule of boundary string is pointed. There's no direct sum on the other side after fusion. So therefore, the fusion of boundary string form a group. This group is called H. And this basically some of the important argument. So you can see that the bulk particle using Tanaka duality, we get a string, we get a group G. The boundary string using the fusion, we get a fusion H. And then the next thing we try to argue this bulk, the boundary string fusion group and the bulk this symmetric fusion category group is really the same group. And actually, this is the main part of the argument. We try to follow this Tanaka's duality argument, proof. Try to put it here. It's kind of long and also technical, so I kind of skip here. But basically, it's using this half braiding between the bulk particle and the boundary string, and assume they can detect each other. Try to show that these two groups is the same.
Sorry, Xiaogang, for the previous slide, can I have a quick question? How do you define the quantum dimension of a string?
Yeah, quantum dimension string again. Yeah, this is thank you. So here I'm using some kind of maybe unconventional way. I don't define quantum dimension string. I define quantum dimension for loop. Somehow I always have a loop, and then I have many loops together, and they are total fusion space. We have n loop fusions dimension for n loop fusion space. They take an nth power, give rise to a quantum dimension for the loop. So here, because string have this, if a string as a segment is difficult, but here I'm really thinking I treated this string as a loops and really constructing fusion space of the loops.
But how do you define it for loops? So the trajectory of a loop in space-time will be some two-dimensional worldsheet.
Yeah, but here I'm using this using trap harmonic. I can imagine I have a one-dimensional trap many loops, and then this trap harmonic have the degenerate ground state subspace. The dimension of this degenerate subspace is a dimension of fusion space of those loops. And the nth root of this fusion space is quantum dimension when n go to infinity. Basically, we have n. Basically, we have n loops, and then the dimension for fusion space of n loops, taking nth root, then that's give rise to this quantum dimension of each loop. Another way you can use in the fusion rule. Actually, in this case, the quantum dimension of this string is a sum of quantum dimension of those particles. That's also works.
Oh, okay, I see.
Yeah. So is it the evaluation on the sphere S2?
It's some dimension, but it doesn't matter because if we take an angle to the limit, the degeneracy from non-trivial color space do not affect this definition.
But Laksha, that's actually exactly the reason I asked. The expectation value of the worldsheet of a loop on the sphere is not well defined because you can always modify the answer by an Euler counterturn.
Mm-hmm.
This is in contrast to the expectation value of the world line of a particle. That's why I was confused how to define the quantum dimension for.
Yeah, so here I think we're using ground state degeneracy, so not using space-time picture. So that means if using space-time picture, the space-time is the time direction is a circle with no non-trivial twist. So when you have non-trivial twist along time direction, there may be actual phase in the partition function with a worldsheet.
Oh, so you probably put it on the torus in space.
On the torus, the space, the time direction with a circle with no trivial, with a constant. So we're doing this only counting degenerate ground state degeneracy. Yeah.
But that makes more sense because on the torus you don't have the Euler counterturn now.
Yeah.
But one subtlety that Shuhe mentioned still exists, right? Even when you count degeneracy, because you can still put particles on the string.
Yes.
That particle may also give you some extra degeneracy.
Exactly. So there's a trouble for the loop. It's a loop may contain particles, and so I need to define some trivial the loop without particle. So means when I shrink, you get identity.
Okay.
Yeah.
I see.
Indeed, this using loop, not using string is have own problems. Yeah. Yeah. So those are shorter way one how to struggle with. Yeah.
Can I make one comment about about the dimension? Maybe there is another another way to define dimension, which is I think equivalent, but you could consider the algebra of these loops and and everything else, and the algebra just of everything else, and you have these two algebras. And there is a notion that is called the Jones index which is basically a notion of the dimension of this small algebra in the big algebra.
Okay.
That is basically equal to the quantum dimension in the examples that are known, and but I think it's a precise definition of the quantum dimension for any kind of set of extended operator. Thank you.
Yeah, thank you for the comment. Yeah. Okay, so to summarize that, if the conclusion for this is that if a particle excitation are all bosons, and using this assumption and those argument, we try to claim that they are one-to-one correspond to this all-string boundary with a point diffusion and with no non-trivial morphism. So that's really the point of fusion two category. and which is basically the Dagravitton theory. Okay. So basically, that's all the 3+1D AB, all boson topological order are classified and realized by Dagravitton theory. And as a consequence, that all the 3+1D twist higher gate theory with all particles being bosonic are equivalent to twist one gate theory. Yeah, go ahead. Yeah.
Can't you consider Dagravitton theories based on two groups? Will they have fermionic excitation?
Yeah, you can. Yeah. So Dagravitton theory based on the two group. If there is no fermionic particle-like excitation, they are equivalent to Dagravitton theory based on one group.
Okay.
That's what we try to say here. All the higher group Dagravitton theory are equivalent to one group Dagravitton theory if there's no fermionic particle.
Okay. Thank you.
I'm a little bit unclear about what is meant by 3+1D Dagravitton theory. A Dagravitton paper is about 2+1D. So what exactly is being meant here?
It's that paper have a lot of things, and here what I mean is there's a part of the paper describing this triangulation of space-time, the finite group, that part. If you think so, here Dagravitton really means the finite group Dagravitton theory. And that one, that construction actually can be done on any dimension.
Do you mean here the main point of that? Well, first of all, Dagravitton is in 2+1, but second, the main point of their paper was adding the H3 term. Do you mean here that you're just doing a 3+1 dimensional gauge theory, or do you need?
Yeah, 3+1 dimensional finite gauge theory with a omega-3 twist. That's H upper 4 twist.
With H upper 4, so that's not what's in their paper, or is it?
Oh,
it's an extension of what they did.
Yeah, it's an extension. Yeah.
Okay,
probably,
so you need both ingredients.
Yeah. We need both. Yes.
No, I think Dagravitton also discuss higher dimension in their paper.
So then it's my mistake.
Yeah. So it's so all this twist higher gauge theory, it's related to this twist one gauge theory. So that's a wonderful consequence of that. And so let me just since time is up, so let me just quickly summarize the result for the fermion case. So actually, this is for the fermion case, that is where the some particle of fermion. So therefore, the group have this kind of a structure. There's some Z2 times this GB with some kind of twist. And so this kind of topology we call the EF topology order. It's kind of emerging fermion topology order. And so the claim is that this emerging fermion topology order is described by the unitary point the fusion 2 category. But here we have some non-trivial one morphism. So basically, we still claim that this topology order can be described by string-only boundary with some simple particles. Okay, and this string on the boundary have a fusion rule, which is given by the GB and the group extent. Actually, this is I should write this way. Yeah. It's a GB extended by some Z2. Okay, and there's some kind of extension problem. And so this is GB. So the boundary string, the GB describes this elementary object, elementary string. And this extending part is describing this Marana string. This P with superconducting string. Okay. And the reason we have this kind of descendant string excitation because we have a fermion. The boundary also have a fermion because the bulk have a fermion. This bulk fermion become boundary fermion. Okay, so the boundary structure is a little bit more complicated. And in addition to the boundary fermion, we also have the bound this Marana string also have this has its own boundary, and this boundary is gave rise to this another particle excitation, which is a quantity dimension 2, a square root 2 Majorana zero mode.
But Xiaogang, sorry,
basically,
in the old boson case, you could have also talked about the descendants, right?
In the old boson, I think there's no descendant because the particles are trivial, and the trivial particle do not form a one-dimensional topological order. You know, if there's a non-trivial one-dimensional topological order, there will be descendant.
Oh, you mean but before you condense all the
before you condense, in the bulk you have a lot of descendant.
Oh, I see.
Bulk you have a descendant. You have a bulk, you have a descendant string.
Right.
Yeah. The descendant string, because the bulk boson carry gauge charge, have emerging symmetry, so descendant string would have this SPT states and also symmetry breaking states. That's a descendant string in the bulk. But the boundary, because the symmetry is all broken, so we don't have that.
I see.
So that makes things simpler.
I see.
So this turned out to be important. Okay. So so let me just skip this. So there are similar arguments. So the point I try to make is the following. And there are two situations. One is that the boundary is the boundary string, the fusion boundary string is just a GB times this Majorana string. So their combination is just really times, and in this case, I'm tempting to drop it. Actually, we can drop this, and so there's a one version of a EF topological order where the boundary string have this simple structure, and I believe those kind of EF topological order can be described as a twisted two-gauge theory. Yeah, and this two-gauge and the two-gauge part, the two-gauge group pi 2 is only Z2. Okay, and so this is a one type. But there's another more interesting situation is that the boundary string fusion have non-trivial fusion. That is the Majorana string attached to the fundamental string in some non-trivial way. This non-trivial can be understood the following. You know, even in the bulk, we have a similar thing. When you have a fermions, you have a Majorana string. And because Majorana string is a descendant, we want to remove them. For example, we want to say, we want to have a string which do not have a Majorana string attached to it. Okay. If you can achieve that, if you can choose a set of a string without a Majorana string, then we can see that all those strings, the three string junction would have no Majorana zero mode. Okay. But however, there is a 3+1D topological order, which is this is impossible. And so because whether a string have a Majorana string or not have a Majorana string, it's hard to say. It's a tosser. We can only say two strings differ by a Majorana string. It's hard to say which string have Majorana string, which string do not have a Majorana string. So sometimes we cannot consistently choosing a basis of string which they all do not contain Majorana string. And this kind of abstraction gave rise to this so-called EF2 topological order. But anyway, and so this kind of EF2 topological order and is really you know have been seen in the fermionic SPT states, and so there's this EF topological order and the fermionic SPT states is very closely related. And they can be obtained by gauging SPT states. So I would summarize the result as following: if you start with the fermionic SPT states and gauge all the symmetry, then we'll get the bosonic topological order, and this will be so-called EF topological order. So we think this so actually result from this work. Really, they are really very much like fermionic SPT states, have a close parallel to that. And it really suggests that maybe all the bosonic EF topological order can be coming from gauging the fermionic SPT states, protected by one group just product by ordinary group. Okay. However, we can also gauge part of a symmetry in the Fermi SPD state. For example, you can gauge part of a GB, not all the GB, just part of a GB. Then we get the Fermi SCD states. If you gauge all the GB, then we get a Fermionic topology order with no symmetry. If you also gauge Z to F, we get this Bosonian topology order, which is EF topology order. So it looks like in 3+1D, even topology order with a symmetry, at least with a group-like symmetry, can be understood in this more general setup. Yeah, thank you. That's all.